América Latina en Foco.
Hi, everyone. Thank you for joining us for the third webinar in the UFFCS America Latina and Foco series from IEEE UFFCS Latin America Outreach Initiative. Before we get started, I again wanted to inform you that this webinar was being recorded. We're excited to have you join us today featuring the topic Acoustic Vortex Beams from Particle Levitation and Air to Cell Manipulation. While we introduce the speakers, I invite you to participate in the Zoom questions that are going to appear before you. For this webinar, we will have a talk given by Dr. Juan Luis Ilau Coelho, followed by Dr. Glauber Silva. Moderating this session today is Dr. David Espindola. During the webinar, please type your questions in the chat box at any time. They will be answered during the Q&A session of this webinar. If you would like to ask a question during the Q&A session, please raise your hand, switch on your camera, and unmute to ask your question. Or if you feel free to type them in the chat box. Automatic closed captioning will be available during the webinar talks. Please press the closed captioning or CC button and choose show caption to enable it at any time during the webinar. I would now like to introduce you to the organizing committee of the Latin America Outreach Initiative, so we'll start with Hermes Camimuro, which is the Latin America Outreach Initiative Chair, Sophie Morse, the Volunteer Engagement Committee member, Andrea Polido, Latin America Outreach Initiative Volunteer, Patricia Cardoso de Andre, Latin America Outreach Initiative Volunteer, and Stephen Lee, who does video editing services. Patricia and Andrea will type these questions that are asked in Portuguese and Spanish to English for the moderator.
It's a show. It's a webinar.
Okay, I think it's me, right?
Yes.
Okay, hello everyone. My name is Hermes Camimura. After a short break in July, we are happy to have you here in our third America Latina in Foco webinar. As usual, you are welcome to, to suggest speakers or be one of the speakers here. Please reach out to us using this email that Andrea is posting on the chat. If this is not your first time watching our webinar, you must be looking forward to our news. We have some announcements for you. Can you share these slides, please? So first, we have I'll ask you to keep you muted, please. Okay, so the next one, so we have our previous webinars available now on YouTube. So please look at the links on the chat box and see the previous editions of this webinar. The next slide. Our Latin America Ultrasonic Symposium had great acceptance. We have almost 90 presentations between oral and poster sessions, and we have a glance of the interests in the region with people, the majority in biomedical ultrasonics and other interesting areas. We also have very special keynote speakers giving joint talks showing their history of collaboration with Latin America and other regions. And then we also have monetary awards in this event for the best student presentations. So if for students that are running or not running for these prizes, stay tuned because we also have a student pitch competition with monetary awards as well. So please join us in this unique opportunity to network and increase the impact of Latin Americans in the UFFC society. The link is also in the chat box. Next, please. Okay. Another event planned by the UFFC Society will occur in October 12 to 22. This is the Summer School Transducers and Waves. And this this is a hands-on course using educational kits, as you can see there. And so the participants will have the chance to learn the main pillars of acoustical imaging using this nice kit. Don't lose this opportunity. The link is also on the chat box, in the chat box. The next one. We have an exciting joint postdoc position available between the interdisciplinary laboratory of physics in Grenoble in France and the Acoustic Institute of Universidad Austral de Chile. And please contact Professor Benoit Coasne and Professor Rodolfo Venegas for more information. Their emails will be in the chat box. Next slide, please. And finally, the UFFC Society has available positions in the administrative committee. Please visit our website for more information and apply for volunteer work using the link in the chat. We also appreciate any help and also, to join also our Latin America outreach initiative. So reach out to us. And now I will hand it over to Sophie. Thank you.
Hello, everyone. It's with great pleasure that today I'm introducing you to our first speaker, Joao Ayalo. He's actually a professor at the School of Mechanical Engineering in the Universidad del Valle in Cali, Colombia. He did his bachelor's in Colombia and then his master's in industrial control systems in Spain. And then he got his PhD in mechanical engineering from the Polytechnic University of Madrid in Spain. And he followed on to found the laboratory in vibrations and acoustics in Colombia. And his current work focuses on exploring different transducer technologies, characterizing materials via non-contact ultrasonic methods, vibrations and acoustics. And he also works on acoustic vortex beams, amongst many other topics. So today we're going to be hearing about some ways of efficient alternatives to generating airborne ultrasound vortexes with high quality. So I'll let you enjoy his talk. Thank you.
Please let me know if you are watching my presentation. Is that okay?
Yeah. Yes, we can see.
Okay, right. Okay, thanks a lot for this introduction and for this invitation. I'll go to the point directly, right? First, I will make an introduction about vortex beams, right? Generally speaking, not for experts, right? After that, I will introduce different alternatives for vortex beam generations, passive and active approaches, right? After that, I will talk about the alternative we've been developed with one of my PhD students, Ruben Muelas, in which we convert these passive gratings into active transducers. And then I will show some experimental results along with some numerical simulations, and then I will show some conclusions. All the experimental results and videos were obtained at our lab, right? So what is a vortex beam, right? Well, a vortex beam in air looks like this when you measure it in a transverse plane at a given distance from the source, right? So the exact definition is a beam whose wavefront is a helicoid, right? And as you may imagine, a helicoid, you can create helicoids of one or several threads, right? If you have a helicoid of a single thread, you say you have a vortex beam of topological charge 1, right? But you can create vortices of different topological charges, like what you can see here to the right, right? So here you have a helicoid of a single thread, and you have a helicoid of 2 threads, right? If you look at this video also, right, the black dots are the particles, right? And what you have is there is a high pressure zone that is somehow pursuing or chasing a low pressure zone. And because of this kind of acoustic fields are called vortices, right? Because they emulate the vortex, right? So in frequency, when you have this field, which is in time domain, right? This video, right? When you see this in frequency, what you get is you get a magnitude distribution of this type, which is pretty much like a donut, right? And you have a dark core, which is a zero pressure core, right? And when you look at the phase distribution, what you have is a singularity right at the center of the beam, right? That means the phase is not determined at this point, right? And if you encircle, if you follow a circular path around this singularity, right? What you are going to see is that phase is increasing from 0 to 2 pi, right? But if you look at this figuring to the right, you can see that depending on the topological charge, that means depending on the number of threads of the wavefront, you can have more than one jump when you follow a circular path around the singularity, right? For instance, here to the right, this is a topological charge 2, and you can see that phase is increasing, right? Increase and then goes down, and again it goes up, and we have 2 jumps between 0 and 2 pi, right? Once you surround the singular point, right? So I'm gonna place this. So right, so this is an experimental wavefront. This is measured in our lab, right, in air, and this is pretty much how it looks like. And here you can see that this dark core, you know, it's all along the principal axis, right? What you get is a kind of a pipeline, let's say, right? Sorry, it's not okay. It's taking time to go to the next one. Right? Why these vortices are interesting? Well, they are interesting because they have the ability or to reconstruct themselves, right? That means if you put an object in the middle of the beam, you know, after a while it will recover its structure, right? Here you can see, you know, this is a video in which there is a vortex beam being generated, and you can see, you know, the object taking the shape more or less of the beam, right? And also, you can use these vortices to understand special features in optics and quantum mechanics. And also you can, as they carry angular momentum, right, you can transfer this momentum to objects and make them to rotate, right? Which is pretty much like here, where you can see that this object is being rotated, or as you could see in this previous video, right? Well, how to generate these kind of vortices? Well, there are different approaches. We have divided these approaches into types. Active approaches, which includes, you know, like you have a transducer with a surface, a helical surface, right? And when you have this type of transducer and the surface is vibrating in thickness mode, for instance, or piston-like, you will get these kind of beams, right? Or you can use the superposition of 2 orthogonal stationary modes traveling in opposed directions. Here you generate one in this direction, and here you generate another one. And if these beams are, you know, they have a phase difference of pi divided by 4, you will get you know, the structure of a helical wavefront, right? Or you can use a phase array, right? And a multi-transducer, and you can generate this kind of effects, you see, right? Or this, for instance, in this case, we are impinging a flat disk, which is an absorbent, acoustically absorbent disk, and we can change the sense of rotation by controlling the phases of the multi-transducer, right? And there are also passive approaches. One quite interesting one is the optoacoustic technique proposed by G. Span in 2004. And what he does is to impinge with a laser beam, which is this red line, impinge a surface which has a helical surface, right? And once the laser beam impinges on the surface, you know, it creates a phase and amplitude distribution inside the material that it's able to propagate in this water tank, right? Also, and more recently, you know, more approaches have been proposed like acoustic lenses and metal surfaces, just to mention the most relevant ones. This works by Giant and Sfalani and Naifi, all of them based on making a beam going through a passive structure, which has a very well designed structure so that the phase distribution along the azimuthal angle is achieved. In this case, they use, you know, Helmholtz resonators. In this case, is Falhani, or I'm not sure if this is the right pronunciation. He uses like all these are waveguides with helical waveguides, and he controls the phase by tuning the pitch of each helicoid inside the waveguide. And this approach proposed by Naifi, in which also uses a waveguide, right? This is the top part of the waveguide, and this is the bottom part. And if you input you enter the sound, the signal here, right? The signal as the sound goes around this circular part, you know, you get this vortex beam, right? Also, using spiral gratings, Jimenez in 2016 proposed using spiral gratings separated by some distance from the active surface, right? The active transducer, also Giant. And in this case, you know, you have all the reflections between the grating and the transducer. And also, you know, this work by Wang, in which he used this is a brass plate in water, right? And he is able to generate a vortex beam by making a beam going across this plate. So now we proposed a new approach, which consists of converting the passive into active. So that means the spiral grating is now a transducer, actually, right? And how do we do that? Well, we do that by using a ferroelectric film, which is metallized in the upper side, right? And what we do is to use a zeta conductive adhesive plastic tape, which is used to glue, to fix this active film, right, to this lower electrode, which was structured with the precise geometry of the grating we are interested in, right? And by doing that, right, we get this type of transducer, right? And well, I will say that this is how a ferroelectric film looks like inside, right? It is a cellular biaxially oriented plastic film, right? And it is only 70 microns of thick, you know. And the method we fabricate is as simple as it is shown now, right? We have the ferroelectrode here. This is the upper electrode. This is aluminum, vaporized aluminum on top of the ferroelectrode film, right? And here we have the PCB, right, with the lower electrode, right? And what we do is to place this tape, which is conductive just in the vertical direction in this case, right? So when we do that, you know, only the active material, the ferroelectric material that is on top of the electrodes will vibrate. This is the velocity profile, you know, this is a sketch of the velocity profile. So in this way, we create a transducer, you know, with the geometry of the grating very quickly, very fast, without having to discretize the material using just a sheet of ferroelectric, right? This is the frequency response of the ferroelectric. I'm not going to talk about this now, but let's go into the prototypes. So our first prototype was this Archimedean grating, right? A spiral grating, right? Which has a pitch. This is the pitch, right? Which is, you know, the pitch of the grating, right? In this case, we create two arms, the red one and the green one, and we can use this grating in this frequency range of operation because of the frequency response of the ferroelectric beam, ferroelectric material, right? So we have 4 turns, right, and 2 arms, and let us see. And so what we did first was to using laser Doppler vibrometry was to measure across the spiral, you know, this way, right? And you can see here the velocity profile as we go along this blue dots line, right? You can see that each time we get on top of the lower electrode, we get, you know, an increase in the amplitude, right? And this is the experimental characterization of the vibratory response. So why this grating is interesting? This type of gratings is interesting because you are able to create, you know, different vortex beams of different topological charge located at different distances from the sources, right? They are concentric, right? They are concentric diffraction orders, you know, at integer values of A, which is the pitch, divided by lambda, you know, and here you can see these different values of A divided by the pitch divided by lambda, right? Which correspond with frequencies, with these frequencies, right? And you can see how, you know, just close to the source, you get a vortex of topological charge 1. But as frequency increases using the same transducer, right? You start having another beam, which is a vortex beam, which is this one, which is now of topological charge 2. But the other one, the one with topological charge 1, is still present, you see? And if you keep increasing the frequency, you will get a third order vortex beam, right? We can see this experimentally. now in this video, right, you can see this is experimental results, right? And you can see how at a given distance, you can get different vortex beams of different topological charge using the same transducer, right? So here we have a case in which we can have the same vortex with using either one or two arms, right? And you can get exactly, for instance, this is a vortex beam of topological charge 2, right? And you can get it using either one arm or the two arms. Also, you can get, two different vortices at the same distance, but using different frequencies. In this case, 70 kilohertz, and you get topological charge 1. Look at the quality of the beam, right, which is quite well defined, and this is because the emitter is not discretized. It's just a continuous emitter. The surface is not is continuous, right? And also you can get at 164 kilohertz a vortex beam of topological charge 2, and at the same frequency and different distances, right? You can see here 3 different topological charges at 240 kilohertz, and you can see now that the quality of the beam is not that good because we are approaching the first thickness extension resonance of the ferroelectric film, right? So we have higher amplitudes, but the quality decreases a little bit, right? So now if we use the two arms, right, we can get similar behavior, right? Again, at integer values of A divided by lambda, there is a new vortex appearing, right? And here you can see the experimental measurements, right? There we have one, and right, okay. Well, and this way we can have vortex beam of different topological charge, easily generated at different distances and frequencies, right? But we wanted to focalize the beam also. So to do that, we used a Fresnel zone plate, which is this geometry. You are here to the left, we have a single arm Fresnel zone plate, and here you have a 2 arms Fresnel zone plate. And using this expression, which controls the geometry of the spiral, right, we can create this type of beams, which is concentrated in a small area in space, in small volume, right? And this, in this expression, this geometry, depends on the topological charge, depends on the focal length. That means the distance at which you want to create the beam, right? So here, for instance, in these simulation results, we have that, for instance, at 150 kilohertz, right, we will have a vortex beam concentrated at a distance of 25 millimeters, right? And if we modify the frequency, you can see that the beam is moving, right? Is shifting, right? And so that means if we control the frequency, we can manipulate, we can steer the beam, along the principal axis. This is the video, right? And you can see how as frequency increases, you can see how the beam shifts to the right, right? This is also experimental results. So here we have a comparison between numerical simulation and experimental data, and you can see that the fitting is quite good, right? And well, this way, that's what we do in order to create, you know, a electroactive grating transducer, which is easy, versatile, and broadband. You could see Archimedean spiral prototypes and also Fresnel zone plate prototypes. We can concentrate, we can obtain concentric vortex beam of different topological charges with low overlapping. We also fabricated focused electroactive diffraction grating, right? And we believe that this fabrication method is easy and useful for broadband application in air, and this approach can be extended to other piezoelectric technologies. Thank you very much for your time.
Thank you so much, Joel. That was really, really interesting. Can I remind everyone to post any questions that you might have in the chat box, and we'll answer them at the end after our next talk. And you can post, you can write them in Spanish and Portuguese as well in the chat box. We'll translate them. So with that, we'll move on to our next speaker, who's Dr. Glauber Silva. He's currently an assistant professor in the Institute of Physics at the Federal University of Alagoas in Brazil. And he received his PhD in nonlinear ultrasonic imaging from the Federal University of Pernambuco and the Mayo Clinic, and then did various postdocs at the Mayo Clinic and the Institute of Pure and Applied Mathematics. And since then, he's also been a visiting researcher in many other countries like Denmark, UK, and France as well. And his interests are in the field of microparticles and cell manipulation in microfluidics, as well as ultrasonic imaging. And today we're going to be hearing about 3D printed acoustic fluidic devices for uses in biospectroscopy applications. And with that, I'll leave the floor to Dr. Silva. Thank you.
Okay, thanks for the introduction, and thanks for the opportunity. Thanks to the organizers for the opportunity to present 3D printed acoustic fluidic devices for biospectroscopy applications. This work is being done here in Federal University of Alagoas with the hands of several collaborators and myself here. And I really think that Latin America Outreach Initiative is a great opportunity for the region to develop in ultrasonics. So with that said, let's go and talk about. So I have three keywords here: 3D printing, acoustic fluidic, and biospectroscopy. Well, each of these words could be a talk by itself, and of course I'm not going to do that. But I'll probably give more emphasis, and you see it in acoustic fluidics. So I'll start giving you some background and what is acoustic fluidics. We just saw the beautiful images and results of waves with angular momentum handling objects. And well, somehow this is related to what I'm going to talk here, in a sense that I'm going to talk about angular momentum, but they have a lot of linear momentum. Yes. But ultrasonic waves have a kind of force known as the acoustic radiation force. And the idea of acoustic fluidics is to use these forces into microfluidic devices. And what is microfluidic device in turn? Microfluidics, you handle fluid portions, let's say liquids, and sometimes gases as well, in micrometer-sized channels. You can think about 100 micrometers as a key scale in the field. So here, it's just to give you a flavor. There is plenty of examples in the internet that you can dig in and look about, like microfluidic devices. But this here is just one more example of a microfluidic device, and you have the scale bar here, 1 millimeter So I want to show you that you have an idea what's the width of microfluidic channel. So you have an idea here. And this was fabricated in a plastic, a polymer. And that was by this group here, which appeared in Lebanon Chip Journal. This gives you a flavor. This actually is to detect the cortisone and the saliva. So you place the saliva drop here, and it goes like capillary effect, and there are different units here. So Acoustic Fluidics wants to join forces with microfluidics, and specifically with ultrasonic forces, or the acoustic radiation force. So what exactly these forces can do in the field? They can levitate things. That's a bit, so you can see drops. You can use water drops here. This is levitation in air, but can be also done in aqueous medium. It can pattern cells and microparticles. These are 10 micrometer beads pattern here. It can separate by size, like larger particles near like 15 micrometers go on top, like in the top channel, and the smaller particles, a bit hard to see, but it goes like up here, goes in the lower channel. And you can deform soft matter like microvesicles and cells as well. So you have a reference for this works here, and this one was actually developed here. And this work was developed also by myself and in a group University of Bristol. So we have a glimpse of what ultrasound force can do for us. So now thinking about 3D printed microfluidics, which is a part that I use to fabricate acoustic fluidic device. Well, the idea is pretty much simple, and I'm sure that all of you have seen this technique work, 3D printing work somewhere. So the basic idea is to have a CAD design here, and it's converted to this standard triangulation language, and then it's converted to slicing, layer by layer, and then eventually becomes an object. There are different techniques to do that. FDM is like fused deposition modeling, ink 3D printing, stereolithography, two-photo polymerization, all of them with advantages and disadvantages. Usually you can reach good resolutions about 20 micrometers and below. That is about to be good enough for microfluidics, but I'm afraid we're not quite there, except when you have a two-photon polymerization, which goes sub micrometers resolution. But there are some drawbacks about this too. It takes too long to print out your structures. So this is the chip that we fabricate here. This is an acoustic fluidic chip with a micro resonator in the middle of this, which is just a microcavity, cylindrical microcavity, and I have microchannels here and LEDs and all that. So I estimate the cost of production of this. So this is a big, strong point in favor of 3D printing methods, about like 80 to 100. It's just like the cost of materials and manpower to do it. It is, of course, if you scale up in the production, you definitely go probably, I don't know, maybe 5-10 times cheaper than this value that I estimated here. So being like a cheap technique, it's a strong point in 3D printed. So it's fast. I mean, you can prototype and you get your device parts right there relatively quick. And it's cheap, which is, well, if you think about microfluidics and acoustic fluidics, this method starts with lithography techniques, which is like over like thousands of dollars if you want to produce like devices. You need like clean rooms and stuff. So here, just doing your bench. And the global market says that 3D printing methods are there to stay. And in 2020 was 13.78 billion US dollars with an annual growth rate of 21%. So I think it's going to be there for a long, long time. So I think this is a 3 features that you may stick with after this meeting when you think about like fabricating device and acoustic fluidics. So it came across our group to join forces with biospectroscopy and acoustic fluidics. So I'll just briefly tell you about like biospectroscopy in particular. I'll talk about Raman spectroscopy, which is a photonic technique that you can read the chemical signature of compounds. And if you think about cells and you have different places, different functions, this is so much necessary to study the biochemistry of cells. And okay, so you can do that by fixing your cells in a cover slide, and you kill your cells. And you can try to do it live cells as well, but it's going to be like drifting with Brownian motion all around. So why not get like the forces of acoustic fluidics and let them do the job for you in the following manner. First, you want to keep cells alive over many hours, if not days. I mean, there are a lot of assays, biological assays with cells that needs to go over like days. In case of Raman, you have the setup here. The idea is actually you shoot a laser, a Raman laser on your sample, and you don't want to get any other spurious backscattering signal. So if you levitate your sample, you get rid of the substrate here, the signal from the substrate, because the laser is tightly focused over like let's say 2 micrometers depth of field. And because the cells will be also aggregated by the ultrasonic forces, you can do single cell analysis, which is pretty much desired by biologists to look for one cell at a time. And you want to keep things with low power consumption, less than let's say 1 watt. The reason for that is you wanted to avoid other effects that can hinder the stability of your trap here, or your levitation state. And also you want to make all this setup portable, at least the acoustic fluidic part. Maybe your cell phone could control and do post-processing right there. Why not? You have great computers right in our pockets nowadays. So let me talk about this microchamber that works as a half wavelength resonator. This is exactly what the name says. I put like half wavelength, a wave with half wavelength in depth here. And when I turn on my piezo actuator, I inject ultrasonic waves in this microchamber. And then I have this half wavelength resonance. So here is the standing wave field. And the radiation force, axial and radial, sets in. And that's it. I mean, so I'll go and I'll beat gravity. So my cells will go up and be there. I have to be careful. There are some showstoppers here, which is this rolls here, is acoustic streaming. So acoustic streaming cause you to have unstable traps. So they arise when you crank up the power of your device. So you don't want to do that. So this is one good reason to make these guys work with low power consumption. Okay, so these guys can kill the stability of your traps. That is much desired to keep all the good features in Raman and cell assay investigation. Here are some expressions for the acoustic radiation force, or ultrasonic forces here. It comes from this configuration as the gradient of an energy. So the force energy is given here, which depends on the acoustic energy densities for potential and kinetic energy density. This can be obtained from the pressure and fluid velocity inside your micro resonator. So if one parameter that you look for, this will end up depending is the energy density, the total energy density inside the cavity. So if you want to maximize the efficiency of your device, you want to maximize this energy here against the parameters that make up your device. So we have some reference for you here. So if you want to check about radiation force, you can refer to some of these papers. There are other, of course, other reference. And so here we have a lateral view, a 2D lateral view of the device, and we have to call for help from numerical methods, finite element methods. Well, the reason is probably clear in this picture because you have a layered a device. So that makes the problem to find the acoustic fields inside your aqueous cavity here complicated. You can try to do a 1D model here, but you're not going to grasp the radiation force, which is responsible to aggregate the cells, and you need that to have a stable trap. So here is the result of simulations. The background image is the radiation force energy. So you have a minimum with the dark blue region here. That means that you have a stable trapping position. So the white arrows are the radiation force field. So you have a particle here is going to be pushed up and will stay in equilibrium in the levitation plane. So, I mean, the bulk of the transducer is a photopolymer resin. And then you have the piezo actuator, which is a PZT5H in our case. And here you have top view of your levitation plane. And you have the white arrows again. Now this time, so you have the radiation force. It points towards the center of the device. So that means if your cell is here, it's going to be pushed, and well, eventually they will occupy space. So they will reach some equilibrium configuration. So then you can start your Raman biospectroscopy and investigate your cell over many hours. Well, the reason is, I mean, this whole device offers you a well-controlled microenvironment. This is about half wavelength of around 3 megahertz. Is about 250 microns height of this chamber, and you have here some 4 millimeters diameter. And you have an idea of the energy scale that we work with, the picojoule. It's really gentle forces, and we go with when you calculate the force, you go to nano Newton. But this is enough to beat gravity for cells. That's great, I guess. And then we did all these simulations in COMSOL software. So the device fabrication goes after you check all this, and they have the device part out of a digital light processing 3D printer. And then you get the parts of your device, and then you do UV curing process. It's not actually showed here, but I just can tell you that you need to go a couple of more hours to strengthen the cure process of your photopolymer resin. This is the parts of the actual device, and you have the PZT standing up here, and you have a scale bar here. So I think you have a glimpse that how then you have to come with handcraft here and do assemble your device with careful. I mean, you need a bit of a skilled operator to do that. Unfortunately, we have one in the group, and then I can jump right on the experimental results here. This is a 10 micrometer polystyrene beads. And then you see here, when I turn on the device, they are actually clustering nicely, and they are already levitating. So I am, let's probably like 120 micrometers on top of my substrate of my device. Here I have red blood cells. I put some cells because we also working with cells in this project. So you see that they cluster as well. We have different pictures, micrographs of this. So here when they reach a steady state equilibrium, so they're ready for Raman spectroscopy, which may take just a few minutes. Then you have a signature of the chemical compounds. So I show you two examples, but in fact, we started this study with people from biology and with leishmanian infection assays. In Latin America, leishmaniasis is an endemic disease. Is a neglected tropical disease. Neglected in the sense that big pharmaceutical companies are not quite interested in do research to find new and more efficient drugs. And so it's endemic in regions of Brazil and pretty much all over Latin America, because it's transmitted by mosquitoes in tropical areas. But what we have done here using our setup with the Acoustic Fluidics device, we levitated and clustered the cells. And then we shoot the Raman laser when you get the spectrum here. So here you have the off that gives you the background signal of the PBS. This is a PBS solution here. And when you turn it on, then you align the laser focal plane and the levitation plane. And then you have all the details of the spectral lines here. And when you do some post-processing here, you have the lines that has correspondence with the chemical bonds. And this is in a very good agreement with previous detected methods that they did by fixing this cell line here, the macrophages. And this is actually good news, because I can pick up this sample and do something else. I can test, because they're still alive after the test. If I fix them, I kill them, and that's it. That's the end. So this work was recently published in Advanced Engineering Materials. So then we introduced this 3D printed devices to assist a Raman biospectroscopy. In another experimental work, and you see the setup here, which is pretty much similar to the previous setup that I discussed for the macrophages and leishmania assay problems. We are trapping red blood cells, and when you turn on the device, those cells are sedimented at the bottom. So they go here with some random orientation. When you turn it on, they become aligned with the axis of your wave, which is vertical, as you saw before. So this is somehow good, because then you see them as like discs, and then you can shoot your laser right on the face of them, and then you have. So this is exactly what we did here. And then we see the lines, like we have two types of cells here: normal cells, just straight for like a blood test, and heated cells over like 70 degrees Celsius. This heat procedure is to get rid of some pathogens, and some studies that people in biochemistry are highly interested in doing. And we could differentiate the spectrum of the heated and normal cells. Here you have like these spikes with different amplitudes, and you can identify some chemical bonds here, which are in a very good agreement with previous results. I mean, blood has been in a lot of different biospectroscopy techniques, such as Raman, and we have very good agreement without any spurious signal, or in a very fast processing. Okay, so to conclude my talk, I briefly showed you some physical principles of acoustic fluidics, in particular acoustic fluidic device. And we also showed a 3D printing fabrication line, specific for micro resonators. That is what we're really interested in this project. We introduced the concept of acoustic fluidic assisted Raman for biospectroscopy, and we actually show it working in a real scenario for important investigations. And I think that one of the most important messages here is there is plenty of work to be done, and specifically to integrate acoustics in micrometer sized devices. There's a lot of challenge to do that. So there is plenty of opportunities to good engineers who wants to join, and applied physicists and chemists wants to join this effort, and I think will pay off in the near future. We need to improve detection methods. We need to make them cheaper. Raman is still a very expensive technique. So if you wanted to have a portable systems, you have to make things portable and cheaper. Otherwise, you may end up having just another benchtop device sitting there. And of course, I mean, all these efforts, you have to develop control hardware. You know, we have these beautiful technologies, Arduino and Raspberry now, and you have to join forces with your cell phone. So I think Acoustic Fluidics has a bright future to help life sciences in different scenarios. So that's the main message that I want to tell you here. And most important thing is the people, and these are the blue students of the group, and they definitely carry on the whole thing here. Without them, it would be nothing. And we have a postdoc, which somebody in between the faculties and the students, which is really a great guy. Harrison, I think he's in the audience there, and this is the faculty people that's really involved and put their souls in this project. I have to thank them all. I have to thank CNPq, which is a Brazilian agency for research and for sponsoring this part of this project. And thank you for your attention. Thanks.
Thank you for that talk, Glauber. I would now like to introduce you to our moderator of today's session, which is Dr. David Espindola. Dr. Espindola is currently an associate professor at the Instituto de Ciencias de Ingeniería at the Universidad de O'Higgins in Chile, and his research interests include the linear and nonlinear elastic wave propagation in soft materials, ultrasound super resolution imaging, and the elastoacoustics in complex medium. I would like to remind you again that questions can be typed in English, Portuguese, or Spanish. If you wish to speak, please raise your hand using the action button and wait for the moderator to unmute you. So with that, I will have Dr. Espindola take it away.
Thank you very much. I'd like to thanks for both speakers. There were pretty amazing talks. Thank you. First, I will keep going with the first questions for Joao. So Glover asked to Joao, what can you fabricate spiral transducer to operate at 1 megahertz in water?
Well, ferroelectrics are in water, they work, right? But frequency response is going to be modified, so we would have to check, you know, the resultant response in water. I already know that a researcher in Spain, Tomás Gómez, is doing experiments with ferroelectrics in water, but he's not. He's using these ferroelectrics for acoustic imaging, right? But I'm not sure if the response he is getting, the pattern, the vibratory pattern of the film is preserved. For sure, I'm sure that we can operate in water, and surely at this frequency, but we would have to check how it goes in order to quantify, you know, the efficiency of the device.
Yeah. Can you comment on the possibility to go to higher frequency on your vortex? I mean, if you want to go to water, then you have to scale up the frequency.
Yes.
And how is possible to do that? It is possible or not?
Well, using ferroelectrics, it's not that easy, because once you put this ferroelectric in water, the frequency, the resonance frequency we are using, you know, we are operating at resonance and outside resonance, right? So if we put this inside water, what's going to happen is that the frequency response is going to shift to the left, right? Mm-hmm. So that's why surely maybe, you know, one of the higher resonances will be useful, but we haven't checked if this resonant response is going to be useful for what we want. You know, this is one of, we have this, you know, this in mind for several years to do it, but still don't do it, you know. But maybe this is the opportunity to explore this and to check how good it would be.
Thanks. Now for Glover. This is a question from Ruben Muelas. I got some questions that came to my mind. First, what are the materials used for the acoustic fluidic device fabrication? That's the first question. Second, how are the cells or samples placed on the device for levitation?
All right. Yeah. Well, for the first question, we use regular photopolymer resins because we use this digital processing 3D printer. So it goes layer by layer in a resin, which is in the liquid state. And then when the light interacts with the photopolymer resin, it becomes harder. And then you go like with the step motor going down and down, and you go layer by layer. So this is a standard material, and probably I should add here that most of this material are biocompatible with cells and other live structures. So, which is good. So, I mean, like you can rely that you have a biocompatible material. Well, the second question is that there's two ways to put your sample in the device. So I showed the inlets and outlets in one of my slides. And so you can go there and you can just use like a control flow unit, or you can pipette your sample there, and it goes through a capillary effect. It's going to push it to the microchamber. Or you can, if you have a single microchamber without microchannels, you can pipette right on top of your chamber, and then you gently place your cover slide. But this is good to test devices, but it doesn't offer you a micro environment with sealed microenvironment, which most of biologists and people in life science want. They want to have controls of temperature. They want to avoid contamination. So you want to be with a device that you have micro channels, that you have an inlet, and you do a flow control, and you place your sample in the microchamber, and then you perform your task that you want to do, and eventually you pick up the sample, and then you go on doing different analysis. So usually this is a type of protocol very much appreciated by biologists in general.
There is one final question from Ruben. He also asked if the device can be autorated at different frequencies. He means the micro resonators.
Well, yes, well, it depends. I mean, in your project. I mean, but usually we start at 1 megahertz, and you can go pretty much up to 10 megahertz, I would say. And then there is like some technical problems start to arise. And the first thing is, if you stick with PCTs, you know that they as the frequency go up, they go very, very thin, and they have some heating effects. So you have to bear in mind that you want to avoid to inject heat flux in your micro resonator, because that can actually cook your cells, and that's not going to be a desirable effect that you're going to tell your life science people. But there are other technologies, lithium niobate transducers, that you can go over. But and then again, you have the resolution of your 3D printer, and you have to bear in mind that if you go under 100 micrometers in height, you probably start experience a lot of bumps, because the resolution of 3D printing is still working to get like micrometer size resolution. So I would say this range for you.
I have one question also. There is any kind of interaction? I mean, for sure there is, but between the pressure itself, the wave and the cell, and I mean, would you be able to detect heating of the cell or something because of the acoustic radiation force or another kind of interaction?
Well, yeah, this is a good question. Let me try to answer it just in a quick review of microfluidics itself. So microfluidics works also with different types of force: electroosmosis, magnetophoresis, optophoresis, and all these forces have advantages and disadvantages. And acoustic forces are probably one of the simplest to implement. Once you get into the field, I would tell you, after some training, it won't take you much time to be fabricating your own device. But I am suspicious to tell you that to moderately understand radiation force is probably the most complicated type of force to be modeled and described, exactly because of what you asked about the interactions of the acoustic fields and thermodynamic fields, which is pretty much temperature, with the objects, with particles or cells. And you can, I'm not quite sure if people have done measurements of, let's say, temperature inside the chamber directly from like radiation force measurements. What I do know is that people use some nanoparticles like rhodamine that they exhibit certain fluorescence for certain range of temperatures. So, and if you inject these nanoparticles in your cavity, which I mean, we started doing that because we're very interested to know the temperature in local temperature, because we want to keep cells alive for most of the time, as long as possible. So these nanoparticles will give you a readout of the temperature there. But you need to new tricks here that we're not dealing with our device now, but it can be done. Just the particles, and you start like working with them.
All right, thank you very much. One last question for Joao. It was here. So Marco Brisotti asked, what is the maximum pressure amplitude generated by the focus device? Can you levitate a small spherical particle with this device?
Thanks for the question, Marco. The pressure we get is around 100 pascals in air, right? We believe we can increase this by 1 order of magnitude by applying higher voltages. We already know, we do know that the film is able to deal with, let's say, 1,000 volts, right? But we haven't yet tried, and the few tries we have done, you know, the voltage is so high that the upper electrode disappear immediately. But we have to improve this in, you know, this technical issue, right? Okay, and now we can levitate, right? To levitate, we are considering now using, you know, standing waves, not progressive waves, right, for levitating, using this type of sources, right? We are sure that we can levitate things, but this is actually the work we are now doing.
Okay, thank you very much. Again, both talks were super interesting. Thank you to both authors. Who's next?
I think that's all the time that we have for today. We so appreciate you all joining us today for our third webinar for the Latin America and FOCO series from the Latin America Outreach Initiative. This webinar will be uploaded to YouTube at a later date if you wish to revisit this webinar or if you missed today's session. Thank you so much and enjoy the rest of your day. Bye, everyone.
Bye-bye. Thank you.
Bye, thanks.
Bye. Thank you.